Ups.
Merhaba hocam.
Merhaba. Nasılsınız Meri Hanım?
İyiyim hocam. Siz nasılsınız?
Ben de iyiyim. Çok teşekkürler.
Ben share screen feature'ını bir enable ettim. Hocam isterseniz deneyebiliriz. Ben burada recording. I would like to welcome you all to the fourth seminar of the AI and CSS seminar series. Today, we have actually a very interesting and a very informative seminar. Professor Dr. Deniz Yuret is with us. It is a great pleasure to be hosting his talk. He obviously does not really need an introduction. I'm sure most of you are familiar with his work, but I would like to start with a brief biography of Professor Yuret. He is a professor of computer engineering at Koç University and is also the founding director of the Artificial Intelligence Center. He holds a bachelor's in electrical engineering, a master's in electrical engineering and computer science, and a PhD in computer science, all from Massachusetts Institute of Technology. He also did a postdoc at MIT's Department of Electrical Engineering and Computer Science. And before joining our computer engineering department as faculty, he co-founded Incura. Professor Yuret's research interests lie in the areas of natural language processing and machine learning. My own research benefited immensely from his work. So I would like to thank again, Dr. Yuret for giving us this talk today. Without further ado, I will give the floor to you, Hocam.
Thank you, Miri. Thank you for having me. So let me share my screen again. Now, this talk was a bit challenging to prepare because we have participants from many different backgrounds, some technical, some not technical. So what I want to do in this talk is basically explain how we got here. I guess we've all heard of AI by now and its impact on various technologies and scientific endeavors. But basically AI didn't come out of nowhere during the last 10 years, even though it actually made a great splash. There's a bit of a history behind it. And I think understanding that history and what the foundations are will hopefully give us a better perspective to judge the developments today. So I want to basically go beyond the doom versus hype discussion that you often see in popular media. You know, you have some authors that are claiming, or some intellectuals that are claiming that AI is going to take over and take all our jobs and stuff. And you know, some people might claim that this is a hype, like some of the other hypes that we've seen over the last few years. Let's judge for ourselves and see what it's all about. So the thing, AI has many different subfields. These include language understanding, machine vision, machine learning, robotics. But basically the subfield that is most responsible for the impact that it's made in the last few years is machine learning. So I want to start by describing machine learning for sort of non-specialist people. So people who already know, please excuse the review. So this is basically my one semester course squeezed into 3 slides. So in machine learning, what we're trying to do is we're trying to learn a mapping from some inputs to some outputs. To make this more concrete, let's assume we're trying to do machine translation, and inputs are English sentences, outputs are Turkish sentences, okay? And we know that humans can do this, so there is an unknown process in the human brain, at least for bilingual speakers, that can turn, you know, these English words to Turkish words, but we don't know how it works. So what we try to do is we try to replace this unknown process, or model this unknown process with a program, okay? So this program has various features that are important technically. So it has to be a parametric program. It has to have lots of adjustable parameters. The operations in this program need to be differentiable. These types of programs are usually known as neural networks or deep learning models. But the important thing is we're basically trying to model this unknown process with a flexible program that can model many, many different mappings from these inputs to outputs. When machine learning starts, we basically initialize this program randomly. So basically, it generates some random mappings from English words to Turkish words. And we introduce something called a loss function or error function. So what is this function? Well, on the top left here, we see the actual input-output mapping. These are the actual translations from English sentences to Turkish sentences, let's say, that are done by human experts. And down below, there is the inputs going through our differentiable program, leading to some predictions. And the loss function or the error function is something that compares the outputs of our program with the desired outputs that we got from the human experts and measures the difference. Okay, so we get a single number at the end for each sentence or for each set of sentences we feed into the system. At the end of this process, we get a single number, and this number basically tells us how far we are from the ideal outputs. Okay? And then basically the rest of the problem is automated. We give this whole setup to one of the deep learning frameworks like PyTorch or TensorFlow, or the one I'm working on called KNet. And these programs take care of the rest. What do? They basically adjust the parameters in this differentiable program in order to reduce this error function. And they keep adjusting it until the outputs of the program look a lot like the outputs of the unknown process we were trying to model. And maybe surprisingly, this method works with great generality. Right now, when you use Google Translate, this is the program that actually, this is the type of program that takes care of the translations. When you actually ask Google a question using your voice, this is the type of program that understands your words. When you show Google your photographs and it identifies different people in your photographs, this is the type of program that works. All of these problems were challenging AI problems during the last few decades. And since we were able to successfully train large enough differentiable programs using this method, we made great progress on all of them. So I'm going to go back and give you some history about how we got here. So I will divide this into 3 sections because these types of deep learning machines, have a interesting popularity graph. They first became popular in 1950s and 60s under the name of perceptrons. So I call this the first deep learning evolution. The machines weren't very deep at the time because there weren't, many computers that had great computational capacity. In fact, Rosenblatt, when he was working on the perceptron, he was an electrical engineer, so he literally built the thing out of wires and spare parts. And on the left side here, you see one of the first problems that he applied it on, which is still a toy problem that we start with in our classes. So you see a giant C letter on the wall, and there's a huge TV camera. And the task is basically to train a machine to recognize which letter is on the wall. So it's sort of recognition of optical character recognition, if you will. So that was one of the first problems. Now, this was created a great excitement at the time. Why? Number one, for a while, for about 50 years, we knew that our brains actually consisted of these functional units called neurons. And neurons pretty much worked by collecting a bunch of input signals from these input branches called dendrites, accumulating these signals in the cell body. And then once the accumulation passed a certain threshold, they send the pulse out from their output channels called the axons. So a perceptron was a really, really simplified mathematical model of a single neuron, if you want to think about it that way. So we basically model all the inputs to the perceptron with a bunch of variables, x1 through xn. We model the strength of each of these connections using a weight, W. So those become the parameters of our model. So we multiply each X with the corresponding W, if you will. These are all numbers in the perceptron. And we add them up in the body of the cell. So we basically have a linear combination of all the X's multiplied with all the W's. And if this sum exceeds some threshold, we output a 1. Otherwise, we output a 0 for some implementations, or -1 in other implementations. That's it. So that's basically a perceptron, a very simple model of a biological neuron. Now, what was new, what created all this excitement, is for the first time in history, we were able to figure out how to train these from examples. Okay, so it's one thing to write a program like this and then somehow figure out, maybe by fiddling and trial and error, what the ideal W's should be, for example, to recognize the letter C or the letter A. But it's another thing to have an automatic learning algorithm and show it enough examples and have some way to modify these weights that eventually the machine learns by itself. So that was the revolution basically perceptrons brought. It was one of the first learning algorithms that worked. So here's the perceptron algorithm. The details are not important. I won't quiz you at the end, I promise. But it's a very simple algorithm. I mean, literally, you look at an example, and if you guess it right, then you don't do anything. If you guess it wrong, then you subtract that example from your weights. So that's about it. That's the whole algorithm in 2-3 sentences. And it's a miracle that this works, and it eventually learns. So mathematicians jumped on the bandwagon, and they actually proved that for a certain class of problems, the learning is guaranteed. After seeing enough examples, this machine always learns the right answer. Okay, but the keyword there is for a certain class of problems. Not all the problems were suitable for perceptrons. In particular, for a perceptron to learn a concept really well, that concept had to be linearly separable, had to have a linearly separable boundary from the other concept. So this is a very simple example. Let's say we're trying to distinguish cats from dogs. And we represent each example, cat or dog, in 2 dimensions, domestication and size. So the first few examples show us that the cats are of medium domestication and small size, and our first dog example is kind of a large size and highly domesticated. And then we get more and more examples, and this line in the middle that I'm drawing between the cats and dogs is basically what the perceptron represents. So the more examples you add to this picture, the line will move to accommodate the new examples. Okay, but at some point, you're going to either get a very large cat or a very small dog or some exception, and basically there won't be a line that can separate the cats and dogs. When that happens, the perceptron cannot learn perfectly anymore because it can only represent lines, and if your data is not separable by lines or in higher dimensions, we call them hyperplanes, then the perceptron won't be able to learn perfectly, and the learning guarantees I talked about that the mathematicians have proved no longer apply. So this was all summarized in a book written about 10 years later called Perceptrons. This was written by 2 MIT researchers, Marvin Minsky and Seymour Papert. And it really basically laid bare all the limitations of these new learning machines. And they listed a whole set of problems that these machines could never learn. And as a sort of our prime hope of creating, human level intelligent AI, people did not take perceptrons seriously anymore after reading this book. And in fact, in the US, the funding for neural net research dried up for at least 10 years after the publication of this book. So there goes our first revolution. It lasted about 10 years. We figured out how a learning algorithm works. We invented an algorithm. Mathematicians proved that this algorithm works for a certain class of problems. And then some other mathematicians wrote a very pessimistic book saying this thing will never solve problems that are a bit more complicated. And then the excitement waned for about 20 years. Okay, so for about 20 years, nobody except a small number of really adamant people worked on neural networks. So that brings us to the second revolution, which started around the time I actually arrived at MIT. So this revolution basically is exemplified by what we call multi-layer perceptrons. This is a very simple idea. This was the sort of book that popularized this idea. The simple idea is this: if one perceptron or one neuron can't learn something, well, obviously our brain doesn't have one neuron. It has a network of neurons that are connected to each other. So why don't we just connect a bunch of neurons to one bunch of perceptrons to each other and form a network of these perceptrons and try learning with them? Okay, so that was the simple idea. Now, why didn't people think of this simple idea for 20 years? Well, of course they did. But as usual, again, the problem was the learning algorithm. So you could actually put together a bunch of perceptrons like this in a network, and you could prove that this type of network structure could learn quite complicated problems, but you didn't know how to train them. The simple perceptron algorithm I showed you in the beginning doesn't work for this machine. Okay, so it was the learning algorithm that was challenging, and that took some time to figure out. But eventually we did. We put some nonlinear functions between layers, technical detail. We basically reinvented calculus. We used the chain rule and said, oh, it turns out we can take derivatives of the loss function with respect to each of our parameters, no matter how deep the network is. And if you're able to take these derivatives using the chain rule, then you know exactly which direction to move each weight in this big system in order to reduce the loss function. Remember, in the very beginning, I showed you this graph where you have a differentiable program that's trying to solve a problem, and then we define a loss function or error function that tells us what the difference between our answers and the real desired answers are. So that was the loss function. Basically, what this backpropagation algorithm does is it finds how sensitive that loss is to each of the weights or parameters in the system. And it tells us which way to move each weight or parameter in order to reduce that loss. And if you basically adjust each of your parameters some small epsilon amount in that direction and keep repeating this, eventually these machines also learn. So that was the backpropagation algorithm. And people proved that it could actually learn arbitrarily complex functions. In fact, mathematicians proved this awesome theorem called the universal approximation theorem, which said there are no limits to what a neural network can learn. So this is literally true. If you have a finite number of samples, given enough units, enough perceptrons that are tied up in a network, you can always learn that particular data set perfectly. So we have to take this with a grain of salt, because if you say, if we found the secret of universal learning, why wasn't AI solved in 1986, right? So if you basically have a super duper learning machine that can learn everything, then that means we can solve any problem. We can teach it how to speak, we can teach it how to see. Well, the issue was in the details, the fine print of this universal approximation theorem. It said it can learn anything provided that we have enough examples, number one. And number two, the network is large enough, okay? So for number one, we almost never have enough examples of the thing we're trying to learn. And for number two, especially for some special problems, the number of units that you need might grow exponentially, okay? So both of those conditions for this universal approximation algorithm to apply might be quite challenging. That's why AI was not solved in 1980s. And about 10 years after the second craze about neural networks started, a mathematician wrote a book called Support Vector, the Nature of Statistical Learning Theory, introducing a different type of learning machine called support vector machines. And this sort of ended, or at least slowed down the excitement about neural networks, because for the problems at the time, support vector machines were actually better. They performed better, they learned quicker, they learned with less data, they generalized better. So people said, well, neural networks, they're fine and stuff, but now that we have these support vector machines, who needs them? So again, except for a few diehards, people switched to other types of learning. Bayesian learning, kernel-based learning actually became big topics in that period. Until about 2012, which brings us to the current revolution that we're in now. So this is the sort of period of deep architectures. That's why it's called deep learning. So what is a deep architecture? A deep architecture is basically just a neural network with more and more layers and more units. Okay, it's bigger and larger. So you might ask, you know, why didn't people in 1986 think of making their networks bigger and larger? They probably did, but they couldn't succeed in training them for various reasons. Number one, the hardware wasn't enough. Number two, the data sets weren't large enough to train the large networks. And number three, the algorithms weren't enough. As you make these networks very large, this backpropagation algorithm of taking derivatives actually becomes more challenging, because the derivatives of the initial layers, or the sensitivity of the loss to the initial layers, might become really small. So you don't really know which way to go with these weights in order to improve the loss. So for algorithmic reasons, for computational reasons, for data reasons, 1980s did not have a deep learning revolution. We had to wait until 2012. What happened in 2012? Well, image processing is one of the main problems that AI has been dealing with since at least 50s and 60s. In fact, one of the stories told at MIT is a professor of mine, Sussman. When he was an undergrad, he went to work at the MIT AI lab as an undergrad research assistant. And at the time, AI lab was just getting started. They have a huge amount of funding from DARPA. They bought all these gadgets, robots, etc. And they had a camera. So Minsky told him, okay, here's a camera, hook it up to the computer and, you know, solve computer vision to an undergrad for a summer research task, okay? So Sussman worked very hard that summer and could not solve computer vision, which is not surprising, because after that we tried to solve computer vision for another 50 years. And, you know, hundreds and thousands of PhDs later, we still haven't completely solved it. So it wasn't a big failure on his part, but he never worked on computer vision again. So that's probably a sad part of the story. And then Marvin basically went to his funders and he said, okay, we need to attack this problem called computer vision, and you need to give us some money to investigate this. And the story goes, the generals at the time who were funding this research said, why don't you just hook up a camera to the computer? And Minsky says, we did. And the generals say, then what's the problem? You know, just look out the camera and see. So you see, seeing and interpreting what we see is such a natural part of the human experience that we don't realize what a difficult problem it is. When a computer looks out a camera in the world, what it sees is basically a matrix of numbers. Okay, so for each location, each pixel in your photograph, there is 3 numbers that represent how much red, how much green, how much blue it is. If I gave you all these numbers and I said, okay, here's a bunch of numbers, please find the cat in this picture, you would have a hard time too. Nobody knew how to basically look at those numbers and figure out there's a cat in there, okay? So this brings us to 2010. So it's been at least 50 years since people have been trying to solve this problem, looking at a picture and figuring out there's a cat or a dog in it. And for the first time in history, some folks at Stanford created this humongous data set called, and organized this challenge called the ImageNet Large Scale Visual Recognition Challenge. This data set had about 1 million pictures, all hand labeled. Okay, so somebody actually sat down and said, okay, in this picture there's a cat, in this picture there is a dog, literally. And so 1 million pictures, 1,000 categories, and a lot of time and effort later, they came up with this challenge. And every year they organized a competition. And this competition attracted the best research teams from around the world. People tried their best algorithms on it. And in 2012, something interesting happened. Namely, the first time entry by Jeff Hinton and his students won the competition. Not only that, but you're basically looking at this chart is the error rate of various programs, and you see, very, very good machine vision research teams from ISI, Oxford, Xerox, Amsterdam. These are used to be the best teams in computer vision, and their error rate is right here, about 26%, 28%, close to 30%. And suddenly, for the first time, this new approach that Hinton and his students introduced cut the error rate in half. They actually achieved 15% error rate in this task. Okay, so that attracted everybody's attention. Not only that, they weren't using any of the algorithms these other guys were using. All they used was a neural network. Okay, so this was basically the one of the first unequivocal demonstrations that neural networks can solve a complicated problem that other approaches fail. So how did they succeed? As I said, big networks is not a very difficult idea to come up with, but it took us 30 years to figure out how to train these big networks. So there's 4 components that contributed to the success. One was the large labeled data set. So in 1980s and 90s, when we actually did research on neural networks, we trained them on hundreds of examples, maybe thousands of examples if lucky. ImageNet had 1 million examples, so that was a big factor. The networks were huge and deep. So I don't know if I can show you this, the real graph here. So these are some neural network architectures from the years following and preceding 2012. So before 2012, one of the first commercially successful neural networks was called LeNet, which was used for digit recognition on sort of checks and receipts and stuff. And the boxes here are not important. They just represent the number of layers of units in this network. So it was relatively deep, but not too deep. And then came AlexNet, which won the 2012 competition. And as you can see, it's quite deeper. And then 2 years later, we had VGG and GoogleNet, and as you can see, they get deeper and deeper. And then in 2015, here's the entries. Okay, so these things were ridiculously large and deep compared to the old neural networks that we used to work with. So this is one reason why it's called deep learning. So this is the third factor, which is GPUs, graphical processing units. So we didn't have GPUs back in 1986. GPUs are basically chips that were invented by companies like NVIDIA for gaming computers mainly, right? A graphical processing unit basically allows your computer or laptop to display, realistic game scenes efficiently and fast. So this technology that was basically invented first and foremost for teenagers to enjoy video games happens to also be good at training neural networks. It turns out this type of graphical algorithm actually relies on a lot of linear algebra and convolution type operations, and those are the exact operations we need to train neural networks. So in 2012, Hinton's student, Alex Krzyzewski, actually took one of the GPUs at the time and wrote a C++ library that basically used that GPU to train this large network. And that's one of the reasons why they succeeded where others failed. Because this type of network not only requires a lot of examples, but it also requires a lot of computation to be trained. And this graph here shows you both the falling error rate over the years in this task, and also the rising number of teams which actually use GPUs and deep learning. And even in 2014, you couldn't actually compete anymore without GPUs and deep learning. And these days, in order to be successful in any area of AI, almost, you need basically the necessary hardware and some expertise in deep learning to apply to your area. All right, so let me skip this for now. What happened since 2012? This was 8 years ago. So it's hard to summarize, but there's a lot of excitement in the air, and the excitement is still continuing. I call this the gold rush, because being a PhD student these days is a lot of fun. There's a lot of old problems that when you try the new methods, you immediately get better results. Okay, this used to be a lot harder before 2010s, and now people basically are applying these new methods to every problem they can find, and beating the state-of-the-art systems. So one of the earliest examples was in reinforcement learning, where DeepMind, a London company later acquired by Google, trained a neural network that's learned how to play old Atari games better than humans, just by looking at the pixels and getting the feedback of the increasing score. It didn't actually know the purpose of the game or the rules of the game. It just randomly played with the joystick and noticed the scores increase. And from that experience, it was able to beat human champions in roughly 50 games out of 80 or something. The same team worked a couple of years more, and they were able to win the world championship in Go. I was actually witness to in 1994, I think, where we beat the chess world champion Kasparov with Deep Blue, the IBM computer. But the way we did it at the time was by a lot of computation. So Deep Blue was able to evaluate 300 million moves a second, and Kasparov's brain, unfortunately, can only do about 100 or 1,000 operations a second serially. I mean, it has a lot of parallelism, but it can't actually compute that many moves. So they were obviously thinking in very, very different ways. And one thing that was obvious to everyone is that in a game like Go, where the branching factor, the number of available moves, is a lot higher, that type of brute force approach would never work. So nobody actually expected us to beat the Go champion in this decade. So a few years before AlphaGo actually beat this, the best Go programs could not even beat the teenage champion of the world. Okay, so within a few years, these guys applied sophisticated deep learning techniques to the problem, and were able to remove another crown from an intelligence game that humans used to be good at. Self-driving cars is a big thing right now, flying cars, self-driving cars. So I'm hoping that my daughter is going to be at the age of getting her driver's license in the next 5 years or so. I'm crossing my fingers so that the technology arrives here and I don't have to teach her how to drive, and you can just tell your car to go anywhere you want. Although Istanbul traffic scares me, I think even AI is going to have a hard time in Istanbul. But this whole thing was made possible again by advances in deep learning. People are training robots for various tasks like walking. I just want to show you this one video though, because when I talk about all the great things that deep learning and AI are making, I'm afraid I'm sort of encouraging this narrative where AI is coming for our jobs, and robots are going to take over and stuff. So this is actually a real robot competition challenge from a few years ago. So it's just basically some examples to show you the state of the art. So even though we can beat the world champion in Go, it turns out walking and opening doors and carrying trays and seeing stuff with your eyes happens to be still very challenging problems, and robots are still not very good at it. So I don't see these guys taking our jobs anytime soon. On the other hand, I also saw the first DARPA competition for self-driving cars, where they basically invited a bunch of research labs and universities to compete on a self-driving car competition. And the first time they did this, within the first kilometer, all the cars crashed, even though they were driving in an empty desert. Okay, so that was the state of the art. The next year, a couple of cars were able to finish. This was like a 200-300 kilometer race in Las Vegas in the desert. And there were some cars which were able to finish. And then 5 years after that, they were actually holding competitions in realistic scenarios with city streets and other cars and pedestrians driving. So the pace of advance can be quite fast as well. So, these robot examples should be taken with a grain of salt, but these are difficult problems. It turns out one of the biggest things I learned from AI, things we usually ascribe to intelligence, like taking integrals and playing chess and doing math in your head, seem to be very easy problems compared to understanding language, being able to see and being able to move. So that's the lesson in AI, if there's any one lesson. So there's a lot more examples I can go through. Speech recognition, we all use it now. Machine translation, I mentioned. One of the things I'm most excited about is multimodal systems, which can handle more than one domain. So for example, vision and language. Well, a prototypical example of this is image captioning systems. So we now have AIs that can look at a picture like this and generate the caption that you see up top. Okay, so this means the AI has to master both seeing, learning how to see and recognize objects in the image, and producing language, and tie these two domains together. So I think that is going to be one of the driving factors going forward in both language understanding and general intelligence systems that combine more than one modality. So here's a little example that we worked on a while ago. I don't know if the sound is on. Okay, I have to. So this is a little piece of work we did over a summer, which turned into a DARPA project for sort of interpreting what you see and describing actions in a video. But what you saw was basically an artificial speaker, right? So you basically are used to seeing these people who describe football games to you over the radio or TV. And this is what we were trying to do at the time. The reason we wear these Star Trek suits was because Sajid, my friend in that video, was in charge of the computer vision, and he wasn't using deep learning, so his algorithms were really bad. So we had to wear bright colors and use a phosphor green ball in order for the camera to recognize what's going on. But these days, basically, we have sort of at the cutting edge programs that can see videos like this and describe what they see. In the other direction, we can also have programs that can visualize what you tell them. So this was sort of the vision to language direction. We can also go the other way in the language to vision direction. This is some work that my student did a few years ago.
Program ilk açıldığında karşımıza böyle bir ekran çıkıyor.
So this is a program that basically is supposed to imagine or visualize stuff that you type.
Şu an sadece kamera ışıkla gerekli. Sol üst köşede ise cümlelerimizi girebileceğimiz bir metin alanı mevcut. İlk cümlemizi girerek programı kullanmaya başlayalım. Maymun odada masanın üstünde duruyor.
So you type the monkey is in the room on the table.
Butona basıyoruz. Ve program girdiğimiz yazıyı anlayıp onu 3 boyutlu bir sahneye çeviriyor. İşte sahnemiz yaratıldı. Daha sonra kamerayla oynayarak istediğimiz açıdan bakabiliriz sahne.
So that's the sort of imagination direction. So this is the direction, if you will, if you're reading a novel or a book of fiction and some things are happening in it, you can usually see what's going on in your mind's eye, and that actually allows you to understand the book deeper and answer questions that are not obvious just from the given text. And right now, computers lack that ability because they can't imagine properly what you're telling them. So they only know about what these words are in terms of their dictionary definitions, or what these words are in terms of all the other places these words were used in. But if we want to do real language understanding, we need to go beyond that, and we need to tie these words to the real world, because text-only methods can only, I believe, get you so far. We need to connect language to the world to make some real progress. This is another example where we teach a robot to navigate using natural language instructions. Again, the robot starts by not knowing any words. We basically show it examples of students. You know, one student basically describes a path, you know, turn right, go up to the lamp, you know, take the road with the wood tiles, etc. And the other student follows the instructions. By seeing enough examples of this, the computer eventually figures out what left means, what right means, what stop means, what go means, etc. And then it can actually understand and follow instructions that you give it. There are some language models that actually generate very high quality human sounding text. But the juries and, you know, the popular thing to do these days is basically journalist interviews one of these language models and asks it questions. If you've never seen one, you can get pretty amazing looking. Okay, maybe we can't. All right, so if you want to see examples of this, just Google GPT-3. That's the latest incarnation of such programs, and they can generate amazing sounding text. We can turn this text generation ability for gaming. When I was young and the computers were not very good at graphics, we used to play text-based games. These are like choose your own adventure type games where the computer describes to you a scene, and then you're a character in a story, and you say go north and, you know, hit the dragon, or, you know, steal the gold or whatever, and then you progress through the story. And now we have AIs that can actually come up with the story as you're typing things, and a lot more creative than what we used to play with back in the day. I want to finish with this, which is the introduction to the deep learning lecture, deep learning class from MIT this semester.
This year, I figured we could do something a little bit different. And instead of me telling you how great this class is, I figured we could invite someone else from outside the class to do that instead. So let's check this out first.
Hi, everybody, and welcome to MIT SICS-191, the official introductory course on deep learning taught here at MIT. Deep learning is revolutionizing so many fields, from robotics to medicine and everything in between. You'll learn the fundamentals of this field and how you can build some of these incredible algorithms. In fact, this entire speech and video are not real, and were created using deep learning and artificial intelligence. And in this class, you'll learn how. It has been an honor to be with you today, and I hope you enjoy the course. voice.
Right.
So a little bit of behind the scenes.
Hi, everybody, and welcome to MIT 6S191.
Hi, everybody, and welcome to MIT 6S191, the official introductory course on deep learning taught here at MIT.
So, and I think that's all I want to say. So we're going to end with the current time period we're in terms of the AI calendar. We're in the third large deep learning revolution right now that started in 2010s. We knew sort of deep models could learn very efficient representations and solve complicated problems, but we didn't know how to train them. But better algorithms, larger data sets, more GPU power enable us to succeed in this task. And for the last 8 years, we've been sort of reaping the benefits of this. What about the future? Sometimes I joke and I say, when I prepared this lecture, I realized, I did some numerology, and I realized that basically every revolution lasts about 10 years, okay? And at the end of those 10 years, a mathematician writes a book, and then people basically don't like neural networks anymore, and there's a 20-year gap. So if we run this forward, I'm going to predict in 2022, a mathematician is going to write a book, and everybody is going to understand deep learning is not ideal, and we're going to forget about it until 2032. So that's my So joking aside, though, I think this time AI and deep learning are here to stay, and the reason I'm saying that is basically they have penetrated all of our technologies and systems, and they have been commercially successful, which is something I can't say for the 80s and 90s. I mean, there were some successes back then, but they weren't as widespread and in as many fields as they are today. So I think both deep learning and AI are here to stay. So we better figure out how to live with them. And with that, I'd like to take any questions if you guys have questions.
Thank you so much, Hojam, for this presentation, which was not only really informative, but also very inspirational. And on behalf of GLODEM as well, I would like to thank you for sparing time for this talk. We can open the floor for questions. We already have 2 of them actually on the chat box. I will read them out loud as people who will watch this later will also get to see them. I mean, hear the questions. Arhun Özkan asked, how was the network structure determined? How many nodes and arcs, etc.? I think this was a question that was asked during the presentation. So I'll ask the second one. Anil Shan is asking, are deep learning approaches used in NLP research? Will deep reinforcement learning approaches have a positive effect on NLP research? Training time seems to be a big problem in reinforcement learning. Can we think that quantum computers could be a 4th revolution in this respect?
Okay, so I will answer yes to the first 2 questions. So yes, deep learning approaches are used in NLP research. In fact, these days you probably can't get a paper accepted to a deep learning natural language processing conference without deep learning in it. Will deep reinforcement learning approaches have a positive effect? Sure. Deep reinforcement learning is getting some surprising results, although it's very fickle and it's a lot harder to train than regular supervised approaches. There are some problems that reinforcement learning is needed to solve, and I believe that also can benefit language. The third, quantum computers, I'm skeptical. Physicists yet need to convince me that they can actually build coherent enough and error-free enough quantum computers to be practically useful. I don't think anybody serious is expecting that to be reality, at least in the next 10 years. So I don't see this in the near term.
So I think Utur Toxos has a question, if you would like to unmute yourself.
Well, actually, it's not me because we're watching two people. So it's Henrik Mullins. So we're two people in the room. But I think maybe he would like to wait a little bit because I see that there is another question.
Somebody else.
So like you can return to us towards the end.
Yeah.
Thank you.
But don't
Okay. I won't. Okay, so the next question is from Esra Bilish. If and how these technologies help us to end pandemic and catch and prepare for the upcoming ones.
So I'm not the expert sort of in the health applications of AI, but I do think going forward, it will have a positive impact. I know, and I have done some work on, for example, microbiology, protein-protein interactions, regulatory gene networks, etc. So biology is a field now that is generated lots and lots of data. And whenever you have a field that generates lots and lots of data, beyond the capacity of any one human to process, then AI comes in handy. So the latest, I guess, exciting development that made the news was DeepMind sort of solving the protein folding problem, which was a big step. This is a problem that people have been trying to solve for several decades now. Those types of advances will surely be beneficial for future health applications.
The next question is from Berke Cesur. Is third revolution actually revolution 2.1 with better hardware and larger labeled data sets?
Okay, so yes, this is a question that's been asked before. Is there really new that we're doing now that we weren't doing in the 1990s? And the answer is, I mean, to some extent, the architectures that are used today, most of them were first thought of in 1990s, but their success wasn't proven until now because of these restrictions. But there are also new ideas. So it's not completely, just scale the old ideas, right? So there, right now, for example, in natural language processing, there's a new architecture called transformers that is breaking all the records. And Google is using it for analyzing your questions and translating your texts. That wasn't invented until 2015. And some of the training techniques, I mean, the actual standard backpropagation algorithm from the 90s literally does not work when you apply it to these deep networks. So you need a lot of bells and whistles on top of that in order to make these things to converge to a meaningful place. So there is definitely a lot of innovation as well.
Okay, we have a second question from Anil Sen, who happens to be one of the researchers of our lab, with really interesting ideas too. So this is not really nepotism, it's just that's the next question. I'm reading it out loud. The popularity of using deep learning methods in many research, especially in the field of social sciences, is increasing. What kind of learning path would you recommend to students in this field? That's an excellent question also for, I think, from our lab.
Right, so double major is the easy answer. I think everybody needs a computer engineering or computer science major in addition to whatever they want to work on. And that will enable you to become a good data scientist, a deep learning engineer, and will enable you to use these technologies yourself. But if you don't have a chance to do this, or you can also do this online, it doesn't have to be an official diploma or anything. There is tons of material online, both to learn programming and computers and deep learning. So a self-study could also get you there. But if you don't have a chance to do either, then you need to collaborate. So our lab, for example, is open for collaboration with all the different departments at Koç. We organized meetings with each group of faculty, with science, with social sciences, with economics, nursing, etc. And in these meetings, we basically discussed, okay, here is the expertise that we have. What are some of the problems you guys think can benefit from AI? And I'm hoping that those meetings will lead to some interdisciplinary collaborations. I am right now collaborating with Erdem Hoca on a sociology project. I'm collaborating with Tilbe Hoca on a language learning project from the linguistics side. So I think this type of collaboration is good both for the AI lab itself and for all the fields that we're contributing to.
And we're also hoping to knock on your door for our project very soon. Erdem Hocam is here to, oh, sorry, there's another question right before that. Emre Taylan Duman is asking, could overfitted model memorize or represent a noisy data?
Right, good question. So overfitting happens to be a big problem in deep learning. As soon as you actually have a very complicated little brain, deep neural network, and you try to train this on some finite amount of data, and all of our data sets, no matter how big we make them, they're still small. What happens is the network tends to memorize regularities in the training data that you may not actually want to use. So my favorite example is, from image recognition. So when people started visualizing what these image processing systems actually did and how they classified cats versus dogs, etc., they wrote programs to see what parts of the image the network was paying attention to when making certain classifications. And they realized for this one model that when distinguishing dogs from wolves, the machine never looked at the animal itself, but the background. So it turns out in the data set, all the wolf pictures were from snowy areas, and all the dog pictures were from non-snowy areas. So the network basically learned to distinguish snow from no snow, and instead of dog from wolf. Same type of thing applies to other applications of AI. For example, this is more recent, I think in China or Japan, a group claimed that they can actually look at a person's picture and figure out if they're going to commit a felony, okay, if they're going to end up in jail. Okay, that was a very controversial statement. But when other researchers analyzed their data set, which consisted of pictures of people from jail and pictures of people not in jail, they just realized that most people in jail don't smile in their pictures, whereas most people outside of jail smile in their pictures, and the network was picking up on that. And that was the, when they corrected for this, the predictive ability of the network went away. All of these are examples of overfitting, and there are things that we need to pay attention to when we're using these new technologies. Just because the network seems to be doing well on the data set you prepared does not mean it's giving the right answers for the right reasons. So you need to actually analyze why it's giving these answers and make sure it's got the right reasons.
Thank you, Hocam. Erdem Hoca has a question. Erdem Yuret, what do you think about the future of the role of domain expertise, especially thinking about the computational social sciences? Will AI tend to become independent from social scientists as a shift from supervised to unsupervised learning accelerates? And future of AI indicate increased social science, computing collaborations, or will AI do the social sciences as well?
Okay, so this is also a very good question and a very common one. My lawyer friends ask me if their profession is at risk. My doctor friends ask me if their profession is at risk. Nobody's profession is at risk. Okay, so AI is really, really bad right now. I know it's progressing and there's a lot of excitement around it. But in order to replace an actual human expert in any field, we're still far, far away from that goal. I mean, eventually, I believe that there is nothing physically preventing us from getting to human level AI, but I don't see that happening in the next decade or two. So all of your professions are currently safe, and I think AI will be a more and more capable assistant in the coming years, hopefully.
Thank you, Hocam. Muhammed Tolga Cangöz has a question. What do you think about Ray Kurzweil's future predictions, especially related to his law of accelerating returns?
Okay, I should say I like Ray Kurzweil. I don't agree with him always, but his first book on AI I think it was called The Age of Intelligent Machines, was one of the reasons I got really interested in the AI area. It's a great book, highly recommended. But most of his later predictions are predicated on this idea of exponential growth. So when you look at various fields like computation per dollar, or the cost of analyzing the human genome, etc., all these technologies seem to be accelerating at an exponential rate. And Ray says if they accelerate with this exponential rate, then in 10 or 20 years, we're going to have an explosion. There's going to be a singularity. Nobody can know what's going to happen next, etc. That relies on a very big assumption. And that big assumption is the exponential will continue, okay? However, in our universe, no exponential ever continues forever, okay? The reason is exponentials tend to go to infinity, and nothing in our universe is infinite. So basically, everything that looks like an exponential eventually turns into an S-curve. Okay, we just don't know when the top part of the S-curve will start. So if that starts in the next 5 years, then we're probably not going to see some of the things he's predicting. But when you actually look at his predictions, just know that he's curve fitting, and the curves that he's fitting are not always physically realistic.
John. The next question is from Jack Loveridge. How relevant was early conceptual work on machine translation by Weaver and Booth and others to the first revolution inaugurated by Rosenblatt? How has machine translation grown up alongside deep learning? Thank you.
So machine translation has an interesting history. So when Weaver and Booth first started this, they basically, tried to get a linguistic solution to the problem, building dictionaries, building grammars, doing it the proper linguistic way. And, that got us to a certain level of accuracy. And in the 90s, we saw the statistical revolution. People said, oh, forget about linguists. Let's just look at the data and build statistical models. And this started in 1988, roughly, and lasted for 15, 20 years. And the reason this stuck around is because it worked. It actually worked better. Statistically learned models work better than human-generated rule-based systems. And then finally, deep learning came into the picture. And deep learning said, basically, throw away all those statistical models. Let's just have a neural network learn this whole thing. Now, when I first heard this, having worked on machine translation a bit before, I was very, very skeptical. I was so skeptical, in fact, I actually took a sabbatical and went to USC ISI to work with Kevin Knight, who was the leader in machine translation. And I spent that year building my own machine translation neural networks. I simply did not believe they would work. I mean, because literally they were saying, you take a Turkish sentence, you stuff it into a neural network, it turns it into a vector, and then you feed this vector into another neural network, and out comes French. Okay, how ridiculous, right? So if a PhD student came to me with this idea, I would probably throw them out of my room. But I went to ISI, we wrote the programs, and they worked. And now I'm used to the idea, so it doesn't seem so incredible anymore. But yes, so there has been sort of 2 breaks in research, and I don't think there's people who know this stuff better than me in the audience, Kemal Hoca, Reyhan Hoca, but I don't think we actually learn enough from the previous stage when we're excitedly working on the next stage. So the statistical guys did not pay attention enough to the previous rule-based, linguistics-based approaches. In fact, the IBM head is rumored to have said, the more linguists I fire, the higher my accuracy goes up or something. And then now that we're in the deep learning area, we're not actually looking at what we learned during the statistical area, etc. So this intergenerational forgetting, unfortunately, happens to be a repeating theme.
I also would like to actually take a moment to thank Professor Kemal Oflazar. I noticed that he actually has posted really important information, useful ones for us in the chat box. And also, if I am missing any questions, please do let me know. I think the next question is from Giray Coşkun. Do you think if the AI research will be dominated by deep learning models or other models will also have an impact in solving the complex problems?
So I think deep learning is here to stay. So it's going to be in our toolbox. It's not going to be our whole toolbox, I don't think. But it's definitely going to be just like, standard search algorithms, standard dynamic programming algorithms were part of our toolboxes all these years. These deep learning modules are also going to be in our toolbox because there are certain functions that we simply cannot write by hand and that are best learned from data. And as long as those functions need to be implemented as part of your solution, you will have these little deep learning modules in your program. Now, is it going to be the whole thing, or is it going to be a component of a larger solution? I don't know. I don't think it's going to be the whole thing. But if you ask me what the final solution is going to be, I have to say I don't know. If I knew, I'd be rich and famous now.
Thank you, Hocam. So as promised, I'm going back to Hendrik Bullens and Utur Soksas. You can unmute yourself to ask the question.
Yeah, thank you very much. Congratulations, chapeau. You are doing really great things at Koç. In order to avoid that my points sound a little bit stupid, I have to tell you that my background, I am an evolutionary economist and cognitive psychologist, and I work in the area of conflict and peace studies, which basically is just about decision-making, problem solving, and prediction. So the areas are very close.
Yes.
Especially what we have in common is the intelligence area. The difference is we in cognitive and neuroscience, we work with natural intelligence, and your field is the artificial intelligence. Now, I will limit my questions to 2 points, which are related. In the part of the second revolution, you said we introduced non-linearity, so different from the first revolution. And you give as an example this decision tree or flow chart, and you talked about this back propagation.
That's right.
But as I understand it, I started, by the way, as a management consultant, and we tried to optimize workflows and things like that. So we used this model in the 70s already and in the 80s. Now, my point is, you said you introduced non-linearity, but in fact, the arrow backwards is about feedback or feed forward. And both are linear. They are not non-linear. And that is connected with my second point, the difference between artificial intelligence and human intelligence. There is a second revolution going on in neuroscience, cognitive psychology, and the whole field. Nobel Prizes like Kahneman, Richard Thaler. So how does the brain work?
Yep.
And the interesting thing is, and that is the second revolution, that, to put it very briefly, it is believed, different from 15, 20 years ago, that maybe 5% of our thinking is conscious and controlled, and that the biggest, far biggest part is automated and unconscious. This thing is that there is no room for that in artificial intelligence. I didn't see anything about it. And now the most surprising thing is, while the human intelligence, the non-linearity, which is said to be in charge of creativity, innovation, and out-of-the-box thinking, is missing in the area of artificial intelligence. There's also the reverse thing. On conferences in neuroscience about the new science of thinking, in cognitive psychology, etc., nobody talks about artificial intelligence. How is that possible? Do you know anything of connections, which are, I think, very much needed?
Thank you for your very informative comments. Yes, cognitive neuroscience is something that I also follow. You know, I'm very interested in. I'm not a big expert on them, but I try to follow the developments because they always inspire us. After all, I must say we're all in the same business of trying to figure out intelligence. Different fields have their different methods. So cognitive scientists try to model real systems, neuroscientists try to model the wet work, and artificial intelligence researchers try to build computational models to see if some of the things we hypothesize actually work or not. I think these are all going to be necessary to fill different parts of the puzzle. Now, in the linearity versus non-linearity comment, I agree that the feedback direction is a linear direction. It's a linear process, but the feed forward part, I can guarantee you, is non-linear, and that's why the universal approximation theorem works, and we can, you know, approximate any function, etc. But that's just the technical point. The other thing you said about unconscious is very interesting. I think one of the mistakes of early AI was to assume that conscious intelligence was all there is. They went around and asked experts how they arrived at their decisions. And they tried to write expert systems with rules and programs to simulate that. But the thing is, if you ask a chess expert or a Go expert how, let's say, they came up with a particular move, they'll tell you a story, but that story is going to be not very accurate. They don't, in fact, have access to all the reasoning and the thinking machinery in their heads in order to give you a complete answer. Similarly, you know, I remember when I was first learning in Turkish lessons about the Turkish grammar and the word structure and the suffixes, etc. at school, I was sort of shocked because I already knew about these things instinctively, but nobody ever actually told me the rules of which suffix was supposed to follow which other suffix. I knew all of this unconsciously, right? So if you actually ask a natural language using person, I mean, we all are experts in language in a sense because we can all use language, but nobody knows why or how they're able to do this. So that, because as you said, all that process is mostly unconscious. I think my personal opinion is that the current deep learning revolution, or the current deep learning models, mostly build systems that look like our unconscious, okay? So we're building systems that are not able to explain themselves, or they're not able to, you know, have concrete steps of reasoning like our conscious thought processes. But we train this network and it suddenly is able to recognize cats and dogs without knowing how or why. So I think the current models are closer to the human unconscious processes than sort of the type 1 system 1 conscious type of processes. And one of the biggest challenges right now is to marry these two approaches. So the old AI people say, look, we spent a lot of time thinking about these type 1 conscious rule-based sequential processes of thinking. And the deep learning people gave it all up. But now they're saying, in order to get the best of both worlds, we need to combine these approaches, somehow be able to chain together a sequence of reasoning, explain our decisions, be able to use language, which are all required conscious processes. And nobody knows exactly how to integrate the two right now.
Thank you very much. I don't see any other questions in the chat box. We may have some additional time if you want, if you would like to ask. I mean, you can also just unmute yourself really and ask if you don't want to use the chat box feature. But if not, then I guess we can conclude the. Oh, I think Dr. Bullens had a question. Because you're muted. Yeah.
If you allow a very brief follow-up question.
Of course.
I think before we talk about integrating the artificial thing and the human intelligent thing, in economics or psychology, Daniel Kahneman, they call it system 1 and system 2. So thinking without thinking fast and controlled calculating thinking, which is very slow. Before we can talk about integrating, we have to find connections first. That is the first step. We have nothing to integrate yet. And the second point is, and it is one of my fields, because you mentioned language and why it is so difficult to translate that in the literary sense into a computer supported thing. I think that is because the words we use are, not only can be, but most of the time are always have a different meaning depending on the intention, the context, the environment, the purpose, etc. So I think what we should need what we need as a first step is a comprehensive theory of meaning. What does meaning? What is the concept of meaning? Because only if you have that, you can start to translate it into something. But the problem will be, as I see it, my research shows me, that the possibilities, the options of different meanings are immense, because the complexity of actors, actions, outcomes, sheer numbers are so complex, are so high, that you have an innumerous number of meanings. So just to
Yes.
I think that we should not forget that. The theory of meaning.
Yes, I wholeheartedly agree on the point you made about the complexity of language. I am sort of, I also agree that a theory of meaning is going to come out of, or eventually be discovered if we're going to solve language. However, I think there is different ways to arrive at a theory, and you can basically be a linguist and analyze humans and try to come up with your theory of meaning. You can be a data scientist, look at lots of text and look at the way people use language and try to come up with a theory of meaning. Or you can be an AI person and you can write programs and see what these programs are capable of and try to arrive at a theory of meaning. So I think all of these are possibly good approaches. None of them have succeeded completely so far. You're right about that. But at least right now, professionally, I'm betting my money on the third option. So let's hope that our camp gets there first.
Sirojam, did you have a question?
I actually do. While you were talking, it just occurred to me that most of the times when we read the press about the latest developments in artificial intelligence, I think the great majority of the publications are either directly informing people, these are the publications in the scientific journals and so on, but in normal daily press, most of the articles you would see are very alarmist towards this.
Yes.
So as a person in the field, how would you suggest that we would recommend the students or the people new in the field to take a position to be neutral and objective towards their stance? I'm a professor of international relations, but I work on the issues of science, technology, and IR. And oftentimes, therefore, I would like to tell my students to follow the latest developments, not only in social sciences or in IR, but also in other fields to have a more complete understanding of the world. And therefore, then I meet these resistances. So what can you tell to help me on this? Thank you.
So thank you for that question. Great question. And I have been approached by journalists and curious students alike to comment on some of these things. So this is a daily problem for me as well. And my recommendation is basically this rule I call the 2-click rule. And I will illustrate this rule with a story. Okay. So about a year or two ago, a news story appeared about Facebook. It said a Facebook research team were working on language, artificial intelligence that generates its own language. And these artificial intelligence agents actually started developing their own language that was illegible, ununderstandable by the researchers, and they had to pull the plug before the runaway AI took over the world or something. Okay, so I read this, and knowing what I know, I didn't take it seriously. I went home. But the next day, journalists actually asked for comments, so I had to educate myself to find out what's going on. So the 2 clicks are as follows. I basically went to the article, and the article actually points to a blog post by Facebook. So you click on that, you go and read the blog post, and the blog post wasn't that ridiculous. The blog post was basically mentioning, they were trying to create 2 agents that can barter. Okay, so it was a very simple game. Agent 1 has a ball and a pen. Agent 2 has a pencil and a bicycle. And agent 1 says, okay, I'll give you the ball, you give me the bicycle, and vice versa. They have this very restricted language, and they're trying to come up with some way to communicate for this bartering game. And at some point during this research, as it often happens in my own research as well, due to some bug in the program or bad training data, the thing actually started spewing out garbage. Okay, so they were generating. So for example, if you try to train a machine translation system, before it converges, you give it a sentence in Turkish, and then the English translation begins da. Okay, so that doesn't mean the AI is getting too smart and inventing this weird language that humans don't understand. That just means the program didn't work. Okay, when that happens, you hit Control-C, you stop the program, you debug it, you fix it, and you restart. That's all that happened. And after that, there's one more click, that's the second click, that actually takes you to the paper that was published. And that wasn't very difficult to understand either. It was a bit more technical, of course, but it basically laid out the rules of the game and the simplicity of the vocabulary that they were using. It was literally a language with 10 words. Okay, so it was not enough to take over the world, I don't think. So after learning all this, I was able to communicate this to the journalists who asked me, but very few journalists asked me. So a lot of the journalists, without doing the 2-click rule, went with the original story written by some irresponsible or I don't know, clickbaity person. These days, I don't know why people do the things they do. But that story got all the clicks, and people subconsciously right now think that there was a runaway AI in some Facebook AI lab and people had to pull the plug. Nothing can be further from the truth. So my recommendation to your students is never believe something without clicking at least twice and reading a bit about the background.
Thank you, Hocam. We have one last question from Anul Shen. Again, as I say, no favoritism here. It happens to be the only question left in the chat box. He's asking, we can model the learning process. Are there any studies modeling intuition?
It depends on what you mean by intuition. I think intuition is just a name we give to the output of a process that we can't consciously follow. Okay, so I read about a paper, I start thinking about a problem, I think, nothing comes to mind, I go to bed, I wake up in the morning, and suddenly intuition, okay, some solution comes to my mind. Now, where did it come from? Okay, so ancient Greeks used to think that there were, these spirits that actually gave you inspirations and ideas and stuff. And I don't think that they were that far from the truth, because yes, they are given to you by things that are not under your control. But what they call spirits happen to be subconscious processes in your own brain, processes that actually continue, under the radar of your consciousness. So if that's what intuition is, then yes, I think we are working on what we're building these days are eventually going to be sort of building blocks for intuition going forward. But in order to call something intuition, you also need a consciousness, and we don't have that yet. So right now, it's not that meaningful to talk about.
Thank you, Hocam. So in the meantime, we got another question from Emirhan Kurtuluş. Do you think that in the future, the growth and the sizes of deep learning models will be restricted by the decreasing level of advancement in computer processing, resulting in a point where the current rate of advancements and discoveries will be unachievable? In other words, GPT-3 was trained on enormous resources, and after building GPT-4, will it become a must to build supercomputers powered by nuclear power plants next to the research center where GPT-5 will be trained?
I never underestimate hardware people. So I remember when I was doing my PhD, this is what, 1996 or something. I had a very, very large language model, and none of the computers in the lab were able to fit this model because I was actually keeping statistics about word pairs. And if you actually, take a reasonably sized vocabulary, 10,000, 100,000, the possible word pairs are huge, and it didn't fit the current memory. And I begged and begged my advisor to get me a super duper computer. He spent about $50,000 that had 2 gigabytes of memory, which was basically what allowed me to finish my PhD. So that was the biggest badass computer at the MIT AI lab 25 years ago. Right now, my phone has more memory. So, and I don't think the progress has slowed down. It changed shape. So the individual speeds of individual chips aren't advancing as rapidly as they used to in the 80s and 90s and 2000s. But then the parallelism kicked in, and now we have more and more computational units in every chip. So I haven't seen that process slow down yet. So I think, if I was to guess, in 5 to 10 years, GPT-3 will be on your watch. So then that means GPT-5 will be also, not that difficult to train. In fact, this is something that I observed over the years. The cutting edge in AI is determined by what a single PhD student can do with the current day's hardware in about a week. Okay, if anything beyond that is unfortunately beyond our science right now, because basically, if you think about it, every new method, every new algorithm takes a PhD student working on this thing, right? And if the turnaround of his experiments, his or her experiments, is more than about a week, then you can't really debug that idea. You lose your concentration, you forget what you were doing, you get a homework, you have to TA and stuff, and that never works out. So if you follow throughout history, the cutting edge methods that were invented, they all correspond to what that particular day's hardware can do in about a couple days to a week. Okay, so that basically limits, unfortunately, our creativity. And that, as that limit increases, the types of things we can do will also increase with it.
Thank you very much, Hojam. We are actually approaching the end of the seminar, but Dr. Bullens had another question. If you have an additional 1 or 2 minutes, could we address that too?
Yeah, no problem.
Okay, if you could unmute yourself.
It's actually me and not him. So this is
okay.
asking the question. Sorry for the confusion. But just to follow up on what you said, like when we are sure of what we see on the internet, it's of course very advantageous and beneficial to go and do these double clicks. But just because you have shown us how deep fake is configured and done,
yeah.
When you were actually showing it, I just wondered, for example, what could be the future of a discourse analysis?
Yeah.
How would a social scientist be able to distinguish Obama's original authentic speeches from the deep faked ones?
Yeah.
So how dangerous do you see, and where is this going? Thank you.
Yeah, exactly.
So currently, we can still distinguish, even if human eye can't distinguish, at least in photographs, we just got to the level where humans have a hard time distinguishing real human faces from fake human faces. We're not at that level at video and voice yet. I'm sure you could tell some imperfections in Obama's face and the tone of his voice. They weren't quite there yet, but we'll get there. And as we get there, then we'll adjust. I mean, if we can't tell the difference, then we're going to have to stop relying on video as evidence. So I think humans are infinitely adjustable and creative in terms of finding solutions to new problems. So that will sort of, get us to a new age where in a court of law, it used to be that if you can actually, here's a recording of this person's voice or here's a recording of their video, then the defense will be able to say, no, that video is fake. And you can't prove otherwise. So that will be, it will not be possible to use those things as evidence.
Thank you so much, Hojam. I think with that, we can conclude the seminar. Again, I mean, I myself really enjoyed and learned a lot in the seminar. It was really thought-provoking, and we also had a really lively debate. So another big thank you goes to our audience for their questions. Hojam, would you like to say any last words?
Well, thank you for coming and bearing with me, and thank you for inviting me, Mary. It was great fun.
It was a true pleasure. Thank you, Hojam. And another note, we have one last seminar before the end of this semester with Dr. Roxana Radu in 2 weeks again. We will be posting further information soon. She is the chair of the Internet Society in Switzerland, and she will be talking about AI governance. So thank you all very much again, and hope to see you. Well, I have to make this joke. See you next year.
Happy holidays, everyone.
Thank you.